So let's talk about the last problem on this sheet. This problem asks you to factor this expression, 6y squared minus 6y minus 72. Factor it completely. So according to the example that we just saw, what should be the first thing that we think about when factoring this expression? Yeah, think greatest common factor. Always check that first. It won't always give you something interesting, but when it does, it's really going to make your life easier as we go forward. So for the three terms, 6y squared and 6y and 72, what do those three terms have in common? What's their greatest common factor? 6. If we find the greatest common factor of 6, which is 2 and 3, 6 again, which is 2 and 3, 72, which if we factor it, we can call it 8 and 9, and then 8 is 4 and 2, the 4 is 2 and 2, the 9. So if we take this all the way down to its prime factors, we may not need to do this every time, but it's pretty easy to convince yourself, I hope, that 6, 6, and 72 have at most a 2 and 3, a single 2 and a single 3 in common. What about the powers of y? How come the greatest common factor there is not going to have any y's in it? Yeah, 72 has no y's in it at all. And when we find the greatest common factor, we always take the smallest number of y's, the smallest power of y possible, and the smallest power of y among these three terms is having no y at all. So the greatest common factor is 6. The constant 6 without any y's involved. So that's good news. It means that we can actually factor out the GCF in a useful way. So starting from our original problem, which looked like 6y squared minus 6y minus 72, we now know that we can take away a 6. And by take away, I guess I mean factor out. And that requires us to answer the question, what's left if I factor out a 6? How many y squareds are inside my parentheses? Just 1, because we've taken the 6 already. How about minus 6y divided by 6? Minus 1y. And then minus 72 divided by 6. Yeah, that's the trickiest arithmetic you'll do on here. If you did the factor tree that we just looked at, you can find that 12 sitting right here, 2 times 2 times 3, the numbers that we didn't choose in the factorization tree. Great. So we've factored out the 6, and that's a big win because now we've reduced a complicated problem to a slightly simpler problem. Our simpler problem now is to try to continue. Try to factor this simpler expression, y squared minus y minus 12. If I can factor that, then I can take this factorization one step further. I can break it down one more level. So, of course, now we have to answer the question, how do we factor an expression that looks like this? Now that the greatest common factor method is not going to avail us, because these three terms no longer have anything interesting in common with one another. So what now? How can we undo, how can we thwart, foil? How do we run foil backwards on that expression? Yeah.
Would you factor y squared into 2 y's?
Great.
And then y is 1y, and since the second y isn't squared, that's the greatest common factor of y squared.
All right.
Y.
So first thing I want to highlight in what you said was how do we know that we're going to be able to use the technique that we're about to use? Which is always the question when factoring, because we're going to learn so many different techniques. It pays to know when which one is going to be useful. Here, we're going to use a technique that's useful whenever we have three terms. So here we have three terms in this expression, a y squared, a minus y, and a minus 12. So we have what's called a trinomial, three terms. And the degrees of the terms are 2, 1, and then there's secretly a y to the 0 here. And so this is also what we call a quadratic expression. Quadratic means that its degree is equal to 2. The highest exponent is 2. So anytime we have an expression that is like this, we can't simplify it down any further because none of these three terms are like terms to one another. So we're stuck having three terms. and it's quadratic, meaning its highest power of our variable is 2, we can use the technique that we're about to use. And the technique begins with the observation that Robert made, which is that when I go and FOIL my answer back out, I need to get a y squared from somewhere. And if I'm going to factor this in a meaningful way, the only way that I can make sense of factoring the quantity y squared is to factor it as a y times a y. So we know for sure that when we factor y squared minus y minus 12 into a product of two factors, I'm going to write it like this, then in each of those factors I should have one term which is just plain old y. So that when I do the FOIL process back out, the product of the firsts, the f and the FOIL, is going to be y times y, and it's going to give me the y squared. That's the first thing that we know. The second thing we know is where the number negative 12 has to come from. Because that number doesn't have a variable in it, there's no y attached to that negative 12, that tells us that that negative 12 is going to have to come not from anything multiplying one of these y's, but it's going to come from the other term in these two binomials multiplied together. The 12 is going to be the lasts. If you like, we can label this the cells in this grid. The firsts, the outers, the inners, and the lasts. It's our little FOIL grid. And so the product of my two lasts, my numbers, has to be negative 12. And this is where the game starts. This is where the game begins. Because we're going to be looking now for two numbers which, when we multiply them together, give me negative 12. That severely limits our universe of possibilities. What are our options for two numbers which multiply together and give me negative 12? Negative 6 and negative 2. So if I'm looking for negative 12, I could do negative 6 and, well, negative 6 and negative 2 would give me positive 12, but negative 6 and positive 2. Negative 4 and positive 3. Also, don't forget things like negative 12 and positive 1. We can also play around with these signs a little. Negative 3 and positive 4. Negative 1 and positive 12. Negative 2 and positive 6. So there's a lot of possibilities still, but at least it's a very small, finite number. There are 6 different possibilities for whole numbers, integers, which multiply together to give me negative 12. And so any one of these pairs could be something that if I put them here and here, will at least multiply together to give me that negative 12. So how do I know which one I want to choose? What else has to happen besides these numbers multiplying together to give me negative 12? They have to add up to negative 1. How come? Where's that negative 1 come from?
The negative y.
Yeah, this term here in the middle, this minus y to the first power. Where's that going to come from in FOIL? Well, in FOIL, we're going to end up with two different terms, the outer term and the outer product and the inner product, the O and the I in FOIL, which are going to be like terms to one another because each one of them is going to have one factor of y. Our O, our outer product, is going to be y times whatever the number is that's in our second line here. So in this example, it would be negative 6y. Our inner product would be y times the first of the two numbers, which if in our example that we just wrote here would be 2y. If I then FOIL that out, how many y's do I end up with in total? From these two like terms. Here I'd end up with negative 6y plus 2y, and that would be negative 4y when I combine those together, which is not what I wanted. Right? When I combine those together, I need to get negative 1y. So negative 6 and 2 aren't going to work because they leave me with the wrong number of y's, even though they give me the right number of constants. Right? They give me the negative 12 that I want, but they don't, when they add together, give me the negative 1 that I want, which is the coefficient of y. So negative 6 and 2 doesn't work. What does? Negative 4 and 3. So that's the pair of numbers which satisfy both that their product is equal to negative 12, but also that their sum is equal to negative 1. So that's the game that we play when we do these factorizations. We try to find a pair of numbers which satisfy both of those properties simultaneously. When we multiply them together, we get negative 12. And when we add those same numbers together, we need to get negative 1. And negative 4 and positive 3 do, in fact, satisfy that requirement. And you can check it. Again, with any factoring problem, you can always check your work by FOILing it back out. And when I FOIL this back out, I get y squared minus 4y plus 3y minus 12. So how many y's do I end up with in total? Negative 4 plus 3? Negative 1, which is exactly the number that I wanted, because that was the coefficient of my y right here. This is definitely something that gets easier with practice. Most of math does, but because this almost numerological game here is something that is often new to you when you start thinking about factoring for the first time, that will definitely take a little bit of getting used to. You don't always have to draw out this little grid, but if it helps you, by all means, do it. I like to use it as much as possible as a conceptual model for how we FOIL something out. And it also kind of helps to explain why what we're doing here is really a reverse FOIL process. We know where the y squared has to come from. We know the negative 12 has to come from the product of the last two things. And so then it's just a matter of finding the right pair of numbers whose product is negative 12 that will also give us a sum when we combine those like terms that accounts for the negative 1 in the middle. So knowing now that we can factor that product in the parentheses as y minus 4 times y plus 3, we then finish by dropping that factorization right in. 6 times the quantity y minus 4 times the quantity y plus 3. And then we're definitely done.